hope you had a good break. We have now, my name is Praveen. I'll be hosting this session. Today we have Huang, Tucker, and Kanchi. They're going to be talking about stream and batch processing at Pinterest. All right, take it away.
Cool, thanks. Thanks everyone joining our session. I'm Heng. Today, my teammate Tucker, Kenchi, and I will talk about Apache Iceberg as a unified storage stack to power batch and stream processing at Pinterest. First, the agenda for this presentation. I will do a quick intro and then briefly discuss Apache Iceberg at Pinterest, and then focus on Iceberg as a unified storage stack, real-time ingestion, and a near real-time and incremental processing. And I will leave 5 maybe to 10, 15 minutes for Q&A. First, what is Pinterest? Pinterest is a visual discovery engine. So every month, over 500 million users across the world come to Pinterest to do shopping, personalized to their taste, find some interesting ideas so that they can do offline, like a cooking recipe, home improvement plans, and also maybe find some interesting creators to follow. Pinterest's mission is to bring everyone the inspiration to create a life they love. Who are we? So we are engineers from Pinterest Data Eng. Data Eng's mission is to provide a scalable and efficient data platform and services to support our business to accelerate innovation. Many of our data infra is built on top of open source project. I think this is Apache Iceberg is definitely a very critical pieces of our data infra. And today I'd like to talk more about Iceberg at Pinterest. So Iceberg, initially I think we evaluated different table formats. So Hive table format was the de facto table format for the Pinterest tables. But I think in early 2020, many alternate table format, better table format like Iceberg, Hoodie, Delta Lake start to gain traction. And it is just a better table format for Hive table format. And we start to evaluate different options, and eventually we choose Iceberg. We did an Iceberg integration at Pinterest, built some use cases in 2022, and then we start to have a massive adoption in the last 2-3 years. So we are the data platform. We provide support of Iceberg in terms of different aspects. So the engines, we integrate Spark, Trino, Flink. These are all open source supported. We just do some tweaks, make it work with our internal environment. And also internally, we support SQL, Java, Python to interact with Iceberg tables. And also we have services for table maintenance services like snapshot expiration, data deletion, data rewrite, delete file rewrite, and so on. For catalogs, I think this is interesting topics and many catalog implementations. At Pinterest, we use Hive Metastore, and also we, since last year, we adopted REST catalog. I think we use GraphTino catalog implementation. Wow, so many people. Thanks for joining. So I think the primary focus of today's presentation is Iceberg as a unified storage stack. So it's not just a better table format than Hive. I think we know the issues with Hive table format. Iceberg solves many of those issues and provide many benefits. But I think from our observations, when we onboard more use cases, Iceberg become more and more important, and it served as the unified storage stack. So why makes Iceberg emerge as a unified storage stack at Pinterest? I think there are two reasons. The first is the Iceberg design principles. We really love the open table format and also engine agnostic, make it easy to integrate with our existing infra. Also, from our use cases, we start to have a requirement to, for example, unlike changes accessed in lower latency, cost efficiency, and data compliance. And Iceberg just becomes a very nice fit to solve all these problems. So let's look at some of our architecture Iceberg before 2022. That is the time before we made Iceberg in production. So our data ingestion and processing architecture look like this. It's kind of, in terms of ingestion, it is like a mini and a batch data ingestion frameworks. We have different frameworks built on top of Kafka consumer client, Spark streaming. We kind of dump the data, DB dump the data. We support different type of databases, transactional databases like MySQL, internal key value store, TiDB. And this batch ingestion frameworks ingest the data to Hive. And then we have Spark and MapReduce jobs processing the full data set, right? So usually the latency is really high. So any changes happen online, the downstream will access that usually after a few hours, and for certain data pipelines, they will access those changes over 24 hours. This is not really good to accelerate many use cases that require lower latency, accessing the online changes. So with Iceberg adopted at Pinterest, our ingestion and processing architecture start to change. So for all the data sources, we all send at the Kafka messages, and we have a Flink to ingest these changes, Kafka messages to Iceberg in a real-time fashion. And our data processing becomes near real-time and incremental process those Iceberg changes. Then let's look at this ingestion and processing architecture in more details. The first is the real-time ingestion. So the real-time ingestion, we have two type of data sources. One is the raw Kafka logs. Usually the logs are generated by the online services. You log some object. This object are usually Swift or JSON encoded. And in our use cases, we have a highly nested struct. Usually has like hundreds of thousands of columns, or sometimes can go to millions of columns. Very nested, can be like 10-level deep nested data struct. This is type of the data we're dealing with. And also the QPS is, and the data volume is pretty large. So we have like over 500 million monthly active users. So you can imagine that the data volume is pretty big. So we have some large data volume like gigabyte per second data volumes, hundreds of thousands of messages to millions of messages per second. Data come to Kafka, just for single pipelines. And our ingestion pipeline needs to process these Kafka messages. We kind of process the data and append the process the Kafka messages to Iceberg continuously. And the output is just the Iceberg table with new snapshot added every Flink checkpoint. So these are the architectures, and we actually did a lot of optimizations, and we also summarized some common patterns we feel are very important to optimize the data ingestion pipelines. The first is we always enable compression for Kafka topic and Iceberg table. Second, we design the table schema and the ingestion logic based on the data access patterns. As I mentioned, we have a highly nested data source. To support faster queries, we usually flatten this nested data, and we apply pruning and filtering to kind of generate a nice table format for downstream to use. And sometimes for some crazy schema, like has over millions of columns, actually it's not that efficient if we just flatten those highly nested schema. What we do, and also depending on the use case, we just read the bytes in and just write the bytes out. Sometimes we want to optimize the table schema. We want to partition the table, so we apply some partial deserialization to extract certain fields that are used to partition the data set, so that downstream processing can be efficient. The third is we also bundle correlated pipeline within one ingestion job runtime. So we have some use cases like need to process multiple Iceberg data sets. So instead of let the downstream job building some coordination or synchronization logic to make sure the data set is available, we bundle those pipelines in the ingestion layer so that those tables are generated. I think the same snapshot are generated within the same Flink checkpoint. We also tune parallelism and the checkpoint interval to avoid the data files being too small. Number 5, we also cut Kafka retention with caution. So usually we want to reduce some infra cost, especially the online infra cost. Cut retention is the way to go, but we have to do this with caution because we have to monitor the Kafka lag. We need to make sure our computing is scalable so that we can handle any traffic spike or traffic increase. Number 6, we have a regular table maintenance like snapshot expiration, data file rewrite. So when we do the real-time ingestion, we are generating a lot of snapshot. By default, every 5 minutes, we generate a snapshot. And soon we are just generating a lot of snapshots. So this table maintenance becomes a must thing to have. Number 7, this is the data loss incident we had earlier this year. So we find like we have to always set the UID prefix in Flink sync builder to avoid operator state lost when job graph topology changes. I think if you haven't done this, make sure you upgrade Iceberg, upgrade the version, and also send the UID prefix. Next, let's look at the database changes ingestion. So the second type of the data sources we have are the online database tables, right? So these database tables all have changes captured at the CDC event, sent to Kafka. And this CDC event, I usually have a few common fields like timestamp, operation, like whether you're doing insert or delete or update, and what is the before and after the content of that specific role the operation applied on. We have the same ingestion pipeline, read the CDC event, apply some complex sanitization logic internally. We develop like the IP mask and also the PI data now out and Central, and then append the process, the CDC event to Iceberg. So I think the pattern is similar to the raw log ingestion. We always append the data to Iceberg, and also we use the Iceberg V1 table format. As output, as a similar table like what we have for the raw logs. There are the CDC event table with new snapshot added every Flink and every Flink checkpoint. And those optimization tips I mentioned earlier are also applied here. But just for this CDC changes, it becomes simple. Usually the QPS is not that much. And I think through our optimizations and different, I guess, some issues we debugged in the past, we're able to build very efficient data ingestion pipelines. So we can handle like so far we test a very large data ingestion. The data sources have 10 GB per second data volumes. We can do that scalably and efficiently. Next, let's look at near real-time and incremental processing. Once the data are ingested in Iceberg, we start to process this data. So the first type of processing we apply is the incremental DB dump. Just remember what we do for the CDC event table, right? We ingest the CDC event table to Iceberg. And now we start to have a couple of Spark SQL queries that do merging to, and then generate add the CDC changes to the main table. The main table, you can think of that as the mirror of the table in the transactional database. So we also have some other processing jobs that run once, for example, like Bootstrap. For compaction, we regularly run compaction jobs. For this incremental DB dump, I think something I want to mention here is for the main table, we are using the V2 format, and we're using the merge on read format, merge on read mode. We actually test copy on write. It works. It actually generate, I guess, a data set that support a faster query, but the cost is higher. We also test directly in Flink, observe the Iceberg tables, but it is generating a lot of equality delete files, so we're not able to handle that. So eventually, we choose the current design. Next, I'd like to talk about near real-time analytics and processing. So as we have all the data in Iceberg, so we have more and more jobs like directly processing Iceberg table instead of reading the online data source like Kafka. So for I think the key difference here is for Iceberg versus Kafka as a data source, the downstream can access online changes in minutes level latency. So instead of like directly reading the online data source, we read Iceberg. The latency is higher, but actually for many use cases, it's just fine. Also, when we use Iceberg as a data source, we have a much cheaper storage cost and also much longer data retention. It actually becomes less stressful to operate the data pipelines because for Kafka, right, you don't have a lot of retention, so you have to make sure your pipeline always have very low processing lag. But for Iceberg data, you don't have that stress, and you can tolerate some like high lag. And also for data in Iceberg, we can have more efficient data loading, like the projection and filter push down make the data loading more efficient. For us, I think we also observe like to process the same amount of data, it just requires less CPU for Flink jobs when you're reading from Iceberg. I think this is all I have. Yeah. Now I think I have more time for questions. Yeah. Mati, what is the
Multifine, like loading multiple table in. So you guys,
Yeah.
are you guys using multifine in Flink? So you can load multiple tables in one shot.
Oh yeah. We have that type of use case.
Yeah. So you talk about this lot of files just streaming, right? How are you managing those files like compaction? You do in ingest or you do a separate process?
Oh, we have a separate process to do table maintenance. For example, I think for streaming ingestion, right, we tend to generate the smaller files. Also, we tune the job to avoid data files being too small, but it's kind of like a small files, like because we also want to make sure the data ingestion pipeline is near real time. So we have a separate table maintenance jobs running to compact the data files to larger data files. And also for the database ingestion cases, we are also generating delete files, right? So we also need to rewrite those smaller position delete file to larger position delete files.
So what's the sizes of the file? Like, when you write, it's
when we rewrite, right? So when we first the streaming ingest, the data size is kind of like a few megabytes. But when we rerun the compaction jobs, where we set the target file size to usually sometime I think larger than 1 gigabyte, so that we can improve the read performance.
Yeah. First of all, good talk. Thank you. Two questions. So first one, So we use the Flink as the ingestion tool for Iceberg. So what's the design choice to choose the Flink instead of other like Kafka Connect?
Right.
That's the first question. Second question is, first one first.
Yeah, I think this is a good question. So actually there are multiple ways to do ingestion, right? So you can have a connector, you can do Spark, you can do Flink. In my opinion, I think every solution should work. We choose Flink because of I think the flexibility and also the processing power of Flink. We can for some I think cases we have to apply very complex processing logics, so we can easily express that in Flink.
Okay, that makes sense. Second question is, how do we provision those Flink jobs? First of all, what kind of API do we use, SQL or this stream API? And do we automatically provision the Flink job when we have a Kafka topic created?
Right. So right now, I think in terms of the API, we use table API and Flink SQL. The provision is not that automatic provision, so we need some like a low-code configuration setup to get a pipeline up and running. Yeah.
So you mentioned that Iceberg snapshots are created during a checkpoint, right?
Yeah.
So like if let's say like there are 10 task managers, does it mean that like there are 10 snapshots generated every checkpoint, or is it just one snapshot which is generated per checkpoint?
Oh, that one every checkpoint generated one snapshot.
One snapshot. Okay.
That one snapshot contains data generated by those 10 task manager, as you mentioned.
Okay. So it's like a post-commit operator, is it, in Flink? Like basically, it recognizes all of the commits made by the 10 task managers.
Right. So the task managers basically generate the data files, right? And when the Flink checkpoint happens, the job manager notifies the task manager, hey, we need to do a checkpoint. Those task manager need to acknowledge, and then start to generate the metadata files, and then eventually all the metadata files go to one task, one operator, and that one operator writes that Iceberg metadata file and also commit it to Hive in our case.
Okay, makes sense. Thanks. Yeah.
How are you managing the read after write consistency in this flow? Is that a problem for you, or so you ingest the data and then you have to read it real time from Iceberg again?
Yeah.
So would that be, how does it work?
I think for us it's not a concern. So I think we actually trying to set the parameters properly. For example, in our ingestion pipelines, we can allow at most one checkpoint at one time. So this avoid multiple checkpoint happens, generate multiple snapshot to the Iceberg table. This is when we ingest the data set to Iceberg. And I think Iceberg itself provided the read-write isolation, right? So I think in most of the cases, we don't see any issues. And for the downstreams, I think what we usually do is we choose a specific snapshot ID to start consuming. So usually we don't have any, confusions about what data you are reading, because you explicitly choose a version of the Iceberg table to start processing.
So the data that you're ingesting can take some time to appear on the read side, and you're saying that's okay?
Yes.
It will be eventually consistent.
Yeah. These are the near real-time pipeline, right?
Got it. Yeah.
Our checkpoint by default is 5 minutes. It means the downstream will, wait at least 5 minutes to read the online changes. But I think this works pretty well for many use cases.
Got it.
I think one thing I didn't mention, I think in the slides is, I think in our data pipelines, we used to have like a streaming pipeline, batch pipeline, right? So streaming directly reading the online data sources, the batch pipeline read the files. But I think with this Iceberg adopted, we start to observe more and more use cases doing near real-time processing, because we ingest the data in real time, generated like small deltas every few minutes, and the downstream can run much faster. And also they don't have to dealing with some like online system issues. For example, you need to configure properly to read online data sources. You need to probably configure properly so that you can enrich your data by calling other services. Those are not that trivial when we build a streaming use case. But when reading from Iceberg, I think things become easy, right? So you just most people use SQL-like the APIs to directly read the data, and they don't have to dealing with many online system stuff. And we see more and more use cases do like this. Yeah.
Thank you.
So for your streaming, can you go with streaming slide of yours, streaming use case?
You want to see the architecture? This one? Or
Yeah, real-time ingestion.
okay.
So in this, do you still have read latency, as he was mentioning, for streaming as well? Is there a gap in between that it takes this much minimum time for you before it's available to read?
Yeah, I think the ingestion latency is one part of the latency, right? So if you are start like a batch job, although you are doing incremental processing, but you have to kind of schedule that job to run. There is schedule latency, and also getting there enough resources to start a job. There are additional latencies. But I think in theory, you can access the data, in near real time on the minutes level latency.
So the back to 5 minutes is the time that you you mentioned.
Yeah, 5 minutes is the ingestion latency. So you're usually you need more time, but it's still on the seconds level. On the minutes level.
Okay, cool. Yeah, thanks.
So I think that's if you are kind of, for example, rely on like a scheduler to schedule your batch job to run. But if you're directly reading the data, right, through the API, I think it just becomes available. You can read, right? So we actually have, I think earlier mentioned, like we have different API supported. We can have a SQL Spark job running. We also have some like jobs like the Java applications directly loading the data. Python can also play with the Iceberg tables.
A question here. Do you run into the commit throughput problem? You know, if there are too many commits to Iceberg, there is a OCC challenge, right?
We actually, I think every time we have one commit. So I think in our ingestion, like I probably missed out, we kind of we make sure that at one time there's only one commit happens.
Oh, so your commit throughput is like single digits per second.
Sorry, what single digit?
So I was just wondering how many commits you do per second.
Per sec, I think I think every 5 minutes we have a commit.
Oh, okay.
But I think, as we're doing this real-time ingestion, every 5 minutes we have one commit. I think you can imagine. So every day we have a lot of commits.
Got it.
We usually keep the data for like 30 days. We have a lot of commits, and that's why the table maintenance is a must to have. We need to expire all the snapshot. We need to frequently run some like data rewrite, and for CDC cases, we also need to rewrite the delete files.
Thanks.
I think one question as a follow-up is, how low can we go in terms of commit interval?
Oh, okay. Commit interval, right?
Yeah.
I think it's like multiple factor we need to consider. We want to avoid small files. So in theory, we can have like we can configure the checkpoint interval like maybe 10 seconds or 20 seconds, but we are generating very, very small files like KB, maybe a few KB. The file is too small. So although we can do that, but I think in practice we don't do that. We still configure at the minutes level because it works well for the applications. Even though we commit more frequent, the downstream do not really need that data. Yeah.
All right. So that's the end, I guess. Thank you, Wang, and entire presentation team. Thank you.
Thank you.